Good morning, good evening, good afternoon, wherever you are in the world, and welcome to another lesson from Ayalaran Academy, delivered to yours truly, Dr. Ade Ayalaran. And this is week 3, lesson 2 of the Physics 101 course. Today we're going to be talking about motion. I'm going to try and move through this as quickly as possible because we don't have a lot of time. Last week we ended off with Newton's laws of motion, first, second, and third laws. Whether you have acceleration or not due to a resultant force is going to result in motion. So how do we measure motion? How do we look at motion? Our primary way of doing that is using graphs of motion. Okay, here I have a distance time graph and a velocity time graph. Just to remind ourselves, there is a difference between distance and displacement. One is a vector quantity, the other one is a scalar quantity. Distance being the scalar quantity can only be positive. It's got magnitude, just magnitude. And if you go around in a circle, even if you come back to where you started, distance measures the total amount of steps or the total amount of spatial movements you have made. Displacement, on the other hand, it has both magnitude and direction. So it is going to matter your reference point, or with respect to your origin, how far you've actually moved. So even if you've traveled a million billion miles in a circle, just because you've traveled a million billion miles, the fact that you've come back to where you started with respect to your origin, your displacement is 0. But the other thing is you can also travel backwards. That's why a displacement graph can have both a positive and a negative y-axis. So on a distance time graph, you can clearly see here that when there's diagonality, the distance is increasing or is changing, so the object is traveling somewhere. When it's just flat like this, the object must be stationary because the distance is not changing. Now, if we wanted to calculate the velocity, so when it's changing distance, there is a velocity associated with that change in distance. We do that by finding the gradient of the line of that section of the journey. So middle school, high school, secondary school, we are taught that to find the gradient of a line, you calculate the change in y over the change in x, and that is what I've done here. So if you wanted to extract the gradient, if you wanted to extract the velocity from a distance time graph, you can calculate the gradient of the line. On a velocity time graph though, similarly to displacement, velocity is a vector quantity, so it has both size and direction. Speed is just a scalar version, and it just has size or magnitude. You can clearly see that wherever there's diagonality, the velocity is changing. So Newton's second law is happening there. There must have been a resultant force which resulted in an acceleration which caused it to change its velocity. Wherever there is flatness, then the object is just moving at a constant velocity or a constant speed. Newton's first law applies there. There is no acceleration, so there is no resultant force. Now, if you wanted to extract the acceleration from a velocity time graph, similarly to the distance time graph, you can calculate the gradient of the line. So where there is a change in velocity, you can calculate the gradient of the line to find out the acceleration during that portion of the journey. If you wanted to find out how far it traveled whilst it was moving, whether it was moving at a constant velocity or a changing one, then you can find the area under the graph to find the distance traveled. Now, we stick with conventional terms. Likewise, as always in physics, every variable, every quantity generally has a symbol or a letter attached to it. Displacement has the symbol S. Velocity, whether it's a final or initial velocity, have the symbols V and U respectively. Acceleration has the symbol A, and time has the symbol T. These 4 or 5 symbols can be superimposed together to give the 4 SUVAT equations. These are equations that pretty much whatever an object is doing, whether it's speeding up, slowing down, however far it's traveling, these 4 equations can describe the motion, and you can calculate, if you know 3 of the other quantities, you can calculate the 4th quantity by using and abusing these equations. The 4th one, S equals ut plus half at squared, is the one most used for projectile motion. Why? If you look at this equation real close, what does it look like? It literally looks like a quadratic. So it looks like an a squared plus bx so ax squared plus bx plus c equals 0 kind of thing, right? That is literally what it looks like. And when you graph a quadratic, it's a parabola. It's a parabola, whether it's upside down or it's up, right side up. So projectiles travel in parabolas. That is why the expression that describes that motion literally looks like a quadratic. And that's very important for projectile motion. So here would be a basic example of a projectile motion situation. Some dude has a ball and he chucks it, right? He chucks it at an angle. Now, projectile motion is describing motion that has both a horizontal component to the motion and a vertical component to the motion. If we look at the initial velocity u that this ball is thrown, we can literally use trigonometry. So remember from lesson 1, we can use trigonometry to decompose it into horizontal and vertical components. The vertical component will deal with what the ball is doing, traveling up and down. And up and down, if I just write a quick note, up, down, you are dealing with gravity. So the acceleration is always g. So g for gravity, or gravitational acceleration. But left, right, you're not dealing with anything except the initial velocity. The initial velocity is going to be the final velocity, because unless you factor in air resistance, which generally you don't, the ball is never going to be affected by any forces or any kind of acceleration horizontally. So the initial velocity that a ball starts with, or an object starts with when chucked horizontally, is going to be the initial velocity that it ends with horizontally. And if I just split this up, so the green arrow is going to show us what's happening vertically, and this blue arrow is going to show us what's happening horizontally. Because gravity slows you on the way up, you can clearly see that the vertical component of the object gets smaller and smaller until you reach the highest point of travel, the height of the motion. And then it starts to fall back down again, because gravity is now speeding you towards the ground. Because you're going towards the ground, you're going to be speeding up towards the ground. And this is literally what projectile motion looks like, and why projectile motion looks like it's moving in a parabola. The horizontal motion never changes, yeah? But the vertical motion does. When you're moving up against the Earth's gravity, you're being decelerated, you're being slowed down. But when you're moving down, according to the Earth's gravity, or down in the Earth's atmosphere, you're being sped up because you're accelerating in the same direction as the Earth's gravitational field. And we shall end it there.